Hello. Yeah, so thank you, sir, for the invitation and for the introduction. So, without wasting much of my time, let me share my screen. Is my screen visible?
Not yet, sir.
But I said it. Okay. Let me try it again. Entire screen. Okay. Now
Yes, sir.
visible now?
Yes,
Yeah.
sir.
Fine. Fine.
Yes,
Okay. So yeah. Okay, so the title for today's talk is Deep Learning for Autonomous Vehicles. So, in this talk, we are going to discuss how the domain of deep learning that you have already discussed in the last 4, 5, I think 5, 6 days, how this domain of deep learning actually helping the research area of autonomous vehicles. Right. So, when we think about autonomous vehicles, the first thing that comes to our mind is how to make a vehicle autonomous. Right, like the cars that we are currently seeing on the road, it's driven by the drivers. Now, the whole point is when we are thinking about autonomous vehicles, how we can remove the part of the vehicles, part of the driver, such that it can run autonomously, right? So, you must have heard this term self-driving cars. So, generally in layman terms, we tell that it's self-driving cars. So, in this talk, we are going to discuss in detail how the different technologies or different algorithms that are there in deep learning is helping the domain of autonomous vehicles. So what? So first thing first, what is an autonomous vehicle? So I just give you a brief about like when a car is driven autonomously. Now the first point that comes to our mind, how a car can actually be driven autonomously, right? If you think about a human driver, when the driver is driving, he has different sensors available to us, different biological sensors when we think about, right? So we have our eyes, we have our ears, we can move our head right and left, even we have the mirrors by which we can see what is happening in the rear end and all. Now because of all these sensors, right, we get the data, right, from our surroundings, and from that data actually we try to create a rough map of our environment, and using that rough map we try to actually navigate the vehicle without any issues. So that is how a human driver actually perceives the environment. Now when we are thinking about a self-driving car, a similar technology we need to employ, where the vehicle should know what are the different kinds of objects that are there in the environment, or what are the different kinds of entities that are there in the environment. Now from those entities, the vehicle needs to create a rough map of the environment. From there on, the vehicle can move, right? Now for that matter, we will see that different kinds of sensors will be used, the different artificial sensors. Now like we have our biological sensors, this eyes, ears and all, we need to use some of the sensors which can work as artificial sensors. So that is where the sensors like this camera, lidar, radar, GPS, IMU, even multiple of these sensors can be used. Like in this picture, you can see this is just an introduction to autonomous vehicles. It's not about just one car. You can see when you are thinking about an autonomous vehicle, there are like a fleet of cars. Like in this whole highway scenario, all these vehicles need to be made autonomous. So all will be equipped with their own set of sensors. Then there should be some vehicle to vehicle communication that should also happen, so that the data sharing could happen and it can help us manage the traffic in a better way. So when you are thinking about an autonomous vehicle scenario, it is like all the vehicles in this a particular scenario needs to be made autonomous, right? Now the question is, it is very futuristic. You can see it is this technology where we are thinking that completely the driver would be eradicated from the scenario, right? So that is not how it works. Actually, it goes through different stages, starting from a stage of 0 to a stage of 5. So I'm going to discuss that in my future slides. So that is what, even if it looks futuristic, it is definitely realistic, because you can see, I think most of you would have gone through some of the videos, YouTube videos, or somewhere you would have seen that vehicles are running autonomously. Although they are not running in a crowded scenario, you can see that they are running in a very controlled scenarios. Okay, so that is possible now. So I will go through different stages of autonomy. There you will understand this whole what do you say, making the cars autonomous, the area of this autonomous vehicle, starting from level 0 to level 5 autonomy. So that is why this system, this autonomous vehicle, and sometimes you will read, when you read the research papers, you will read like it is autonomous vehicles, or even they call it as advanced driver assistance systems, or ADAS system. Because you will see that there is a computer system that will actually help the driver in some way. So it is not like today we are completely driver driven car and tomorrow it is going to be completely driverless car. That is not going to happen. It is not a 0-1 problem. Starting from zero, we need to go at different steps, then we will reach to the last level. So at different stages, when the level of autonomy increases, you will see that there will be a computer system which is going to help the driver in some way. That is where the driver assistance comes into picture. That's why the whole system in short is known as ADAS systems or advanced driver assistance systems. Now coming to level 0 autonomy, as I already told in my previous slide, it goes through different levels, right? So level 0 autonomy is the one which we are currently seeing on the road, where the driver is fully responsible and permanently carries out all the aspects of the driving, right? So that is what is level 0 autonomy. So in this case, there is no computer system like we currently see on the road. There is no computer system that actually manages all this, right? Now when it comes to level 1 and level 2 autonomy, it is known as assisted mode. That means some kind of assistance will be given to the driver. And you will see that, so before actually going to that, you will see that whenever there is a autonomous vehicle, there are actually three main components. One is the steering, by which we actually move left or right. There is this braking system by which we apply the brakes and the car stops, and then there is throttle or accelerating system by which we actually apply acceleration to the vehicle. So if all these three components can be made autonomous, then the vehicle can be made autonomous. That is how we think when we are thinking of making a car autonomous. If we can delegate all these three tasks to a computer system which can do all these three tasks even done by the drivers, then we can then think of like we can make the vehicle autonomous. Now you will see that as the level of autonomy increases, the slowly the computer system or the whatever the system that is there in the autonomous vehicle, that will help us to achieve those tasks. So in level 1 autonomy, what you are going to see is that the driver can delegate either steering or acceleration or braking to the system. That means any one of the three will be delegated to the computer system. Whereas the other two tasks will be done by the driver itself. So that means the driver can delegate either steering or braking or acceleration to the system. The system will perform one of the driving tasks, whereas the other task will be performed by the driver himself. Then in case of level 2 autonomy, which is again part of the assisted mode, the driver must permanently monitor the system. Okay, in this case, he can delegate all the three tasks, whereas the driver need to permanently monitor. That means it is like the software is not robust enough to fully let it run the autonomous vehicle, right? So in those cases, the driver needs to completely monitor the system. The system will perform several of the driving tasks, in some cases all the driving tasks, but not to a greater accuracy. We can think of like that. Like there are many tasks that are involved to make this vehicle autonomous. So we will go through all these tasks one by one. There you can understand. So you can think of like the software we are making is not up to that level, so that we can just leave the computer system to handle it, right? So in those cases, the driver must permanently monitor the system. So you can see from level 1 to level 2 autonomy, some kind of autonomy has increased. Now when it goes to level 3 autonomy, which comes under the automated mode, you will see that in certain situations the driver can turn attention away from the road, but must always be ready to take full control again. So in those cases, again, the software system that we are talking about is more robust as compared to the level 2 autonomy. So in those cases, the driver can turn his attention away. He can see, if he sees that there are not much traffic on the road, he can just turn his attention away, maybe talk to the fellow passenger, something like that he can do. But at the same time, he has to monitor. That is always there, because the software is not that much robust. Again, the system can autonomously control the vehicle on defined routes. That is very important. So in some controlled scenarios, like in some factory scenario or in some campus scenario, the vehicle can be made autonomous. You will see that most of the research that is currently going on, you can see that they are in the level 3. Even some vehicles are in level 4, so I would say that it is between level 3 and 4. So in case of level 4 autonomy, which comes under autonomous mode, even level 5, the final one, comes under autonomous mode. So in case of level 4 autonomy, the driver can transfer the complete control to the system. So this is very important, because he can completely transfer the control to the system, but also devote himself to other activities, like he can drink some coffee and talk to the passengers. But however, he can take the control at any time if he wishes. So that is the difference between level 3 and level 4. In case of level 3, he has to take control whenever needed, but in this level 4 autonomy, it is up to his wish. That means the software system is more robust as compared to the level 3 autonomy. In this case, the system is able to perform all driving tasks. All of the driving tasks that you are currently seeing, that can be done by the level 4 autonomy. Even you would have seen some demo videos from different companies like Tesla and other companies who are working in the domain of autonomous vehicles. You'll see that they are currently working on almost in level 4 autonomy, because they are able to run it in some controlled scenarios, whereas they can even talk to someone, and even they can make videos and everything. But coming to the final stage, that is the level 5 autonomy, is the one that we want to achieve. That is where the no driver is needed. That means there is no driver seat. It is like a complete vehicle, autonomous vehicle, where every seat is a passenger seat. You can think of like some scenario where a passenger enters into the vehicle, and just he needs to tell like where he wants to go. Then the vehicle will automatically find out the path, where which path it should follow. Even you can give some path, like I want to go to some medicine shop, then I want to go to a destination. Then based on that, it will find out what would be the best path that can be taken, and the vehicle will run, right? So that is what we want to achieve. That is the level 5 autonomy. I can see that it is very futuristic, but believe me, in some countries they are actually planning to make autonomous vehicle corridors where the vehicles can run, right? So it is definitely realistic. It is maybe in next 10 to 15 years it is going to come. So that is why there is whole lot of research that lies in this domain of autonomous vehicles. Now coming to the software architecture, so as I told you, there is a computer system which actually take all the decisions. That means there will be a software architecture that is followed by the whole algorithms, right? So there is like three main components that are there in the autonomous vehicle software architecture. One is the sensing, then the computing, then the actuation. So sensing is the one by which the autonomous vehicle senses the environment. So there are different kinds of sensors for to do that, like this camera sensor, which we already know. I think many of you would have gone through different articles, or even some of you are doing research. They would know what a camera sensor can do. You can get the visual information of the scene, right? So there is a camera sensor. Even in some cases, multiple of the camera sensors can be used. We will see how that can be done. Then there is another sensor, that is the LiDAR sensor, light detection and ranging. Okay, so we'll see how LiDAR sensor actually helps in the domain of autonomous vehicles in a far better way than the cameras can, right? So that also we are going to see. Even there are like these radar sensors are also there, right? Then there is IMU sensor, inertial measurement unit, and GPS sensor, and other sensors can also be used. But my point is that there would be different sensors that would be connected to the autonomous vehicle, and from there the data would be collected. So that component is known as the sensing component. Then comes the computing component. Again, in the computing component, all the computation helps. So again, it is divided into three different parts. That is, first part is the perception part, then the decision part, and then the planning part. So in the perception part, which is the short form for perceiving the environment, like a human being enters into a unknown scenario, what he or she does, he will first see the environment, how it looks like, what are the different kinds of objects that are there. Now from those objects we will try to find where they are and what is my location with respect to others in the environment. So that is the part where I try to localize myself. Now once I localize myself in that unknown environment, I'll try to move around, right? Even when we are driving an driving a completely mechanical vehicle, that is what we do. Let's say we enter into a scenario which we have not seen. Of course, there are different static objects, there are different dynamic objects that would be there. So let's say you enter into an unknown environment with a car. So what do first? You first see the whole environment, how it looks like. Now from there on, we try to create a mental map, and from there on, we try to move around. Right? So that whole process is known as the perception. You perceive the environment, right? So actually that whole process is perception plus decision plus planning. But the component where you try to access the whole environment by creating a mental map, that process is known as the perception, right? So again, inside the perception, there are different kinds of components are there: localization, detection, and prediction. So localization is the part where the car tries to know different where it is with respect to others. So that is the short form of localization, locating yourself with respect to others in the environment. So the car tries to locate itself with respect to other entities in the environment. The entities could be static entities, or like these buildings, or the trees, whatever that comes on the highways. Even it can be dynamic obstacles, not obstacles, dynamic objects like these cars, or buses or different kinds of vehicles, we could say, and the pedestrians or bicyclists. It could be anything, right? So we first the car tries to localize itself with respect to others in the environment. Then the other part is detection, where the car tries to detect what are these kind of objects, right? So it can be like, as I told you, it can be cars, buses, vans, bicycles, trucks, or other objects, right? So that is the part detection comes into picture. Again, when it comes to any robotics environment, right? So it is not about just detecting through a camera. We need to detect in 3D. So those who are familiar with the process of images and all, they would know that images can give you only 2D plane. So whatever the objects that you are going to detect, that will be in 2D plane only. We will not actually get the depth. So doing detection only on the camera plane is not going to help. That is why I told you that this lidar sensor, which can give you the data in 3D environment, that is very important. So that is where we are going to see another extension to the 2D object detection. Some of you must have heard is the 3D object detection. That will be much more important in case of autonomous vehicles. Then comes the prediction part. So now once you detect and localize yourself with respect to others in the environment, we need to know where the other objects are heading. So then only we can know if that heading means we need to know their trajectory. So once we know the trajectory of different vehicles in the environment, then only the autonomous vehicle can take a decision like where it should move with respect to others. Like if we know after some time where the other vehicles would be, I can take an accurate decision where the vehicle, my vehicle or the autonomous vehicle should move. So that is where the prediction part that comes into picture. Then once all of this done, that is where we create, as I told you, if you make it analogous with a human being, so or the human driver, that is where we try to create a mental map of the environment. For example, let's say when you are driving a car, some car is there in your front and it is slowing down. So what you do, you try to access what would be the different, like you try to access what would be the trajectory of that vehicle by detecting at what speed or what deceleration it is decelerating. Then from there on, you try to access where the vehicle would be after some time, and you try to take a decision like whether to move to the left, whether you need to slow down, whether what kind of decision that needs to be taken. That is how it is done. So that is so the first part is to perceive, to know where the vehicles are and what would be their allocated, or what do you say, what would be their predicted trajectories with their velocities and acceleration and everything. That is the part perception. Again, the same thing that I told you in case of a human driver needs to be replicated in an autonomous vehicle. So that is where we do this part of like perceiving the environment. Then once the perception is done, then it goes to another component called as the decision component. Again, in decision, actually the decision needs to be taken how the vehicle should move from one state to the other state, or one position to the other position. That is again done based on the output that we get out of this perception system. So once you get the localization, then you need to take a decision like how the, or what can I say, how the vehicle can move from this position to a safe position, right? That is the decision component that comes into picture. Even like as I told you, let's say vehicle is slowing down, your decision could be you need to slow down depending upon whether there is any vehicle to the right hand side. If you are working in a Indian scenario, you need to see whether there is a, because generally we take the we don't take overtake through the left hand side, right? We take overtake to the right hand side. So we need to check whether there is any vehicle on the right hand side or not. If there is any vehicle, then you need to little bit slow down, or you need to, if you want to overtake, then you need to go right and overtake. So those kind of decisions needs to be taken. That means let's say you want to overtake, that means there is some position on the right hand side where the vehicle can move to a safe state, right? So that decision needs to be taken. So how the vehicle can move from one position to the other position, that decision comes under this decision component. Then once that decision is taken, so till now the vehicle has not moved, only the decision is taken that this vehicle needs to move from position A to position B. Now the question is how the vehicle should move from position A to B. Sometimes you can move fast, sometimes you need to go slow. So all this planning needs to be done. So that is where the planning component comes. So you see, from perception, first the sensing is done, it goes to the perception component. From perception it goes to the decision component. From decision it will go to the planning component. So in case of planning, again it divided into two parts: mission planning and motion planning. Again, mission planning can be of two types. One is the global mission and the local mission. So global mission is like, as I given an example, when the passenger enters, want to go from place A to B, maybe some stops would be C and D and all those things. So that is the global planning, where the vehicle tells you that this is the path that we will follow. So that is the global planning done by the autonomous vehicle. But while moving, it will encounter different kinds of objects. It needs to deviate from its original path and and what do you say, safely navigate different kinds of objects that are there. Now once it deviates from its original global path, again once it avoids different kinds of obstacles, as you can say, once it avoids that, again it needs to go to its original path. So that is where local mission is also there, right? So mission planning is of two types, global mission and local mission. Then comes the motion planning, which is very important, because as I told you, to move from one position to the other position, the different kinds of what do you say, velocity profiles that you could follow, like you can move with a higher velocity, we can be move with a lower velocity depending upon scenarios. If you are in a very crowded scenario, you need to go very slowly. If you are in a height based scenario, you can move fast, right? So those kind of motion parameter needs to be set. So here we can say different kinematics parameters like this, acceleration, velocity, all these things need to be set. Right? That is where the planning components comes into picture. So all of this mission and motion planning parameters need to be converted to a command. Okay, so that command will be generated. So what you can think, the output of this computing component is a command. So you see, from sensing component, the data is sensed. In the computing component, all this perception, decision, and planning will help you to find a command which will move from one position to the other safe position, one safe position to the other safe position. Right? So that is how a human brain also works. Now, once that command is generated, that will be given to a actuation component. Okay, so the actuation component is responsible for actually moving the vehicle. So that is the part, the third part, the actuation component is the part where actually the vehicle moves. So till the time of sensing and computing is all about like getting the data and computing inside the autonomous vehicle. Now once the command is generated, that command will be given to the actuation component. There actually different kinds of controllers are there. I will not go into details of the controllers because I don't work in those domains. As a computer science researcher myself, I generally work in the domain of computing, right? So where different kinds of computation happens. So in my future slides, we are actually going to see how the computing component works, and more specifically how the perception component works. So that is where my research lies. So I will go into details of how different deep learning algorithms actually come into picture in the domain of perception in autonomous vehicles. So again, in some research papers, if you go through it, you will find the term perception. Even you can find this term as a situational awareness. Okay, like how the autonomous vehicle try to aware itself with respect to different situations that it encounters, right? So commonly known as perception. Even you will encounter this term called as environmental awareness. Okay, so this environmental awareness, situational awareness, perception, all are same. Okay. So it's about how the car senses the environment around it using the different sensors that we already saw, like camera, LIDAR, radar, GPS, IMU. These 5 sensors I'm mentioning because these are the 5 basic sensors that are needed for an autonomous vehicles. But apart from that, there could be other sensors like this ultrasonic sensors in some cases. In some cases, the radar could be short range radar, long range radar, even multiple types of LIDARs and cameras are used. We'll see how that can be done. But the whole point is huge amount of data can come, because there is not only, you can see camera sensors are nowadays very even low cost. At the same time, the data is not that much, what do you say, in terms of size, it is okay. It's not that much heavy. But when it comes to other sensors like LIDAR, it is a very costly sensor. Along with that, the data is also heavy. Right. So when I say heavy, means it is like how to process that data, the kind of data that comes into. So it is like data heaviness, how we can handle that. So that is where the huge amount of data comes into picture, and all the data that comes with this kind of what is sensors, it's not relevant. We need to discard the information that is not needed. Only we need the information that needs to be processed to get the better perception capability. So that is where we are going to see how we can do it, and that is where we will again see these deep learning algorithms are much more important. Again, this sensing, thinking, and acting. So this the computation component, you can think of like a thinking component, because that is where the algorithms run. So the sense, think, and act, actually you can think of like this is the sensing, this is the computing, and this is the actuation part. All happens in a cycle way, like one after the other, one after the other, one after the other, till the time the vehicle moves from one position to the other position. So these are the different kinds of sensors that I told: the camera sensor, Using camera sensor, I think if most of you are from the domain of computer science, then you know that this kind of, even from other domains, they are now familiar with this technology like object detection. Okay, so using camera, we can do the object detection. Then we can also do the semantic segmentation. I'm going to discuss all of them one by one in my future slides and how deep learning is helping that. Then we can do the traffic light detection. That is also one of the main components when you are driving an autonomous vehicle or even a vehicle nowadays. If you drive, the traffic light detection is one of the components that we do. We need to know where the traffic light is, what is the color of the traffic light. Based on that, we need to take that decision, right? Then lane following, if you're going through a lane, how to maintain that lane. That is also one of the areas that we can do using this camera sensor. Now using the LiDAR sensor, we can extend actually whatever we can do with the camera sensor, but more specifically the task that is done with the LiDAR sensor is the 3D object detection. Because as I told you, in case of a real life scenario, we need everything in 3D. Just by knowing that a vehicle is in front, it is not going to help. We need to know what is the size of the vehicle. So it depends, like let's say a motorcycle is going and a car is running. In your a motorcycle is moving in your front and a car is moving in your front. We need to know different dimensions, right? So that is very important, and that is what is very important. And using camera sensor, we would not know that, because camera sensor lacks the information about depth, even the scale. Okay, so we would not know what is the length and width and height of the vehicle only using the camera sensor. So we need some sensor which will actually work on the drawback of the camera sensor, that is the depth information is missing. It can work on that drawback to give you some information that can actually give you 3D information. So that is where the LiDAR sensor or the light detection and ranging sensor comes into picture. We are going to discuss again. I will show you one of the LiDARs also. So then there is radar sensor, which is very efficient in finding the velocity of different vehicles. So you need to know, like in your mind, when you are running a vehicle, in your mind, you find what would be the approximate velocity of different vehicles, right? So similar to that, we need to find the velocity of different vehicles on the road. So that is where the radar sensor comes into picture. Then there is GPS sensor, which is the global positioning system, which puts the autonomous vehicle in global frame of reference. So it will give you a latitude and longitude so that you can know, you can actually be placed in the global map. So sometimes this global positioning system helps in knowing the position of other vehicles on the road, so that if those vehicles are not directly visible to you, you can actually find out their approximate position and you can take some decision, right? So that is where the GPS helps. Then there is inertial measurement unit. So the inertial measurement unit, or the IMU sensor, actually provides the acceleration and gyroscope measurement. So acceleration of the vehicle that we are running, that is very important. And gyroscope is like what is the heading of the vehicle and with respect to the global north and global east. That information we can find out. So you can see this camera, LiDAR, radar, or ultrasonic sensor, if you come into picture, or the multiple types of other sensors if you use, they are like active sensors. They take the active data from the environment. So they are known as active sensors. The GPS and IMU, everything known as a passive sensor, because it directly doesn't interact with the environment. They just give you the information about the vehicle, right? About the own vehicle, not the vehicle on the road and all, right? So that is why this camera, LiDAR, radar, and everything are active sensors. GPS and IMU are passive sensors. Then comes a very good research area in the domain of in the autonomous vehicle, is the multi-sensor fusion. Because you see, camera sensor has its own drawback, like it can't give you 3D information. So we are coming to LiDAR, but again, LiDAR is not foolproof. LiDAR has so many disadvantages. So in those cases, camera is going to help. So it is not like camera is we are fully removing the what do you say, dependency on the camera sensor. We are just saying that in some cases LiDAR might help, and in some cases camera might help. So that is where this area of multi-sensor fusion is very helpful. So that is where you will see that camera plus LiDAR fusion can be done. Even LiDAR and radar fusion can be done. We are going to see how that can be done. But this multi-sensor fusion is one of the main components in the domain of autonomous vehicles. So if you see an autonomous vehicle, this is how you are going to see different kinds of sensors. So you will always see that LiDAR sensor will be placed at the top, because LiDAR sensor is a 3D sensor. It gives you three-dimensional information. So if it gives you three-dimensional information in 360 degrees, actually it can give you information in 360 degrees. So that needs to be placed on the top. So you are going to see a LiDAR sensor, which is a cylindrical sensor, placed on the top of the autonomous vehicle, so that it can take information from 360 degree in 3D. Generally, the camera sensor, if you are using only one camera sensor, that is placed on the front. Okay, we can even place it on over here. If you are if you just want to get the frontal information, like a human being, generally we get the information from the front, right? we can move our heads, but very rarely we can move our head like 360 degree to see what is going behind, right? So that is the reason if you are using only one camera sensor that is generally placed on the top, sometimes that camera is movable like our human head can, okay, so that can be done. But sometimes what happens is that like this Tesla car, what they are doing for their autonomous vehicle, they are using multiple of camera sensors with overlapping field of view. Like you can place 6 camera sensors with the overlapping field of view to cover the 360 degrees. That can also be done. So depends upon how you want to achieve your goal. So if you want to use like multiple cameras that can cover the 360 degrees, then you can place the cameras on the top. If you want to cover only the frontal part, then only one camera can be placed on the front that can cover your frontal part. So that is how the camera sensor is placed. Generally 360-degree cameras are not used. So generally you can see in the previous line I told you that we use multiple of cameras with overlapping field of view. I didn't say that we can use only one camera that can cover 360 degrees. That is very problematic, because if you use a 360-degree camera, you are not going to get the actual information about the scene. Generally you get the fisheye images and everything that is generally rounded, and it doesn't contain the actual scale of the environment, right? So that is why generally we use the rectilinear cameras. When I say rectilinear, means the camera can give you rectangular images, right? So if you place rectangular images, it can't sorry, if you want rectangular images, it can't cover the 360 degree. So that is where you use multiple cameras with overlapping field of view. At the end you try to create how the 360 degree would look like from the camera sensor. So that is how the camera sensors are placed. Then there is other sensor, like you can see this radar sensor, which is generally placed on the left hand side and right hand side. Again, there are two types of radar sensors can be used, like the short range radar sensors, which can give you the velocity of near about vehicles, and these long range radars, which can actually place to know the velocity of different vehicles near long range, right? Then apart from that, we can have additional LiDAR units. Like in this case, generally this is not a costly LiDAR that is put on the down. Generally the LiDAR that is placed on the top is a 3D LiDAR sensor, very costly sensor. But this LiDAR sensor which is placed on the down is generally to know whether there is any speed bump or potholes and everything. So that is why generally 2D LiDARs are used when they are placed over here. But apart from all these sensors, GPS and IMU are of course there, and they are passive sensors. They don't want active information from the environment, so they are generally placed inside the vehicle. So apart from GPS, IMU, and all these sensors, there is a computer system that lies behind. You can see, and all these sensors data are being collected by the computer system, where actually all these information are being processed using different deep learning algorithms. Then a command is being generated to pass it to the vehicle, and that vehicle can run autonomously. So that is how the whole autonomous vehicle works. Now coming to the different kinds of algorithm that I already discussed in case of with respect to different sensors. The first is the camera sensor. Now using camera sensor, we can do different kinds of tasks, and you will see that in all of these tasks, you will see that mostly these deep learning algorithms are being used. For example, let's say we are thinking about 2D object detection. Why 2D? Because as I already explained, in case of a camera sensor, we can get only an image of intensity values, and then the depth information is missing. So when it comes to 2D object detection, it is like how we can detect that object. So when it comes to object detection, it is like we need two information. One is the what kind of object it is, and what is its position inside the image frame, right? So that is where you get a length, sorry, you get a bounding box along with what kind of object it is. For example, let's say a car is moving on the front, you need to know what kind of object it is. So it will say that it's a car object. Along with that, it will tell that what is its position, like the bounding box that encapsulates the whole object on that image frame. So that is where it is a 2D object detection is a classification, if though as well as regression problem. So those who are familiar with the concept of machine learning, they will know what is a classification and regression, right? So classification task actually finds out to which object does it belong, whether it's a car or a truck or bicycle or pedestrian or auto rickshaw or anything else on that road. So that is where the class or the classification comes into picture. Regression is the part where it tries to find out the bounding box. When I say bounding box, means there will be some XY position, along with that width and height would be there, right? Because we are in a 2D plane, so there will be some width and there will be some height that is again in the pixel plane. So you have a classification as well as regression problem, right? So that is why 2D object detection are a very specific kind of task where you perform both the tasks. So again, if you go to the algorithms, there are different kinds of algorithms in this. There is this RCNN algorithm is there, then single shot detector or SSD algorithm is there, and more specifically, most of you would know this YOLO algorithm. You only look once. Again, if I want to go through these algorithms one by one, they can even take more than 1 hour to explain all these algorithms. So in this talk, I am not going to discuss the details of these algorithms. That will take too much of time. I'll just tell you what are the different kinds of algorithms that are there. Those who are very much interested, they can actually go through these kind of algorithms. They are readily available in the papers are readily available. Even if you go to YouTube and everything, you will find the authors' videos and everything. That also they can go through. But more specifically, they task it to do the object detection. This YOLO object detection is very famous nowadays because they're working in real time. They can give up to, like, if you are using a graphical processing unit, they can give up to like 45 frames per second. The latest version of YOLO, which is YOLO V8 or V9, I don't know. It started in the year of 2017, but now it is at a stage where it can give you very high accurate object detection. So that is where most of these test systems use it. But having said that, this YOLO algorithm, although algorithm wise it is very robust, but as most of you know, right, the machine learning, your machine learning algorithm is as robust as your data set is. If your data set is good, then your algorithm, if it is a good algorithm, it will work in any kind of environment. But the YOLO algorithm is generally trained in like foreign scenarios. So using a dataset called as COCO dataset. So once you bring the YOLO pre-trained weights and work in Indian scenarios, most of the objects are not going to be detected. For example, these auto rickshaws, they are like very specific to Indian and I would say the South Asian countries, right? So these auto rickshaws or the kind of cars and car structures, truck structures, bus structures are different from the foreign scenarios. They are not going to be detected properly. So if you want to work on the YOLO algorithm, generally what we do, we collect our own data, then we label the data, then we retrain the YOLO algorithm, then only these algorithms can work, right? So that is where the 2D object detection, although it is very there are algorithms which works up to a very good or good accuracy, still there is scope of research in this area. Then comes the 2D semantic segmentation. The 2D semantic segmentation, again I am using this term 2D because it works on a camera plane, because camera plane can give only the 2D information, not the 3D information. Here the pixel wise classification is done. So the difference between 2D object detection and semantic segmentation is that in this case of 2D object detection, we try to find out a bounding box, and whole of this bounding box belongs to one class, right? But in this case, each pixel on that image will belong to one class. So like there would be pixels from the sky, there would be pixels from the trees that are there around. You can find the pixels from the buildings. Apart from, you will find pixels from different dynamic objects like the cars, buses, by pedestrians and everything. Even you can find the pixels on the road. Now each of these pixels will belong to one class. Like all the pixels belonging to road will be given one class, all the pixels belonging to the sky will be given one class, like that. So we will actually find out the outline of the object. So in case of, you see, in case of 2D object detection, you are not able to find the outline, rather you are able to find out only the bounding box. But in case of 2D semantic segmentation, actually the outline of the objects can be found out. So that is where the, again, most of the deep learning algorithms, like there is a like segmentation algorithms can be used. There is a data set called a DeepLab V3. Okay, so that okay, there is an algorithm DeepLab V3 that is most generally used for 2D semantic segmentation on autonomous vehicle data, and there is a data set called a Cityscapes dataset which gives you the data for semantic segmentation in autonomous vehicles. Okay, so this is the using the YOLO algorithm I was talking, like 2D object detection. So you can see the dog is given a bounding box which encapsulates this, the green bounding box which actually encapsulates the dog object. The pink, sorry, so this bounding box actually encapsulates the bicycle object. This bounding box actually encapsulates the car object, right? So that is how the 2D object detection output looks like. When you will go to actually real scenarios in the sorry, when you actually go to the highway scenarios, you will see that this kind of objects you can get, like these cars, motorcycles, this auto rickshaws, bicycles and everything. But you can see it is not fully detecting. Like this car is not able to detect, this motorcycle is not able to detect. The reason being the lighting. You can see the COCO dataset is not trained on like very adverse scenarios. So when you are driving an autonomous vehicle, many adverse scenarios can come, like it is raining, or it can be snowy, even it can be like at night also you can run the vehicle. So how to do proper 2D object detection in different kinds of environment, different kinds of roads, that is where the research actually lies for 2D object detection. Okay. Then in 2D semantic segmentation, you can see this is the output of a image. Okay, now you can see all the pixels belonging to the sky it's given one color. That means all the pixels belonging to the sky belongs to one class. All the pixels belonging to the car is one class. You can see it is given a red color. Even the buildings are given one color. The trees are given one color. The road is given one color. That means the pixels belonging to each object are given one color. So by doing that, you actually find out the outline of the objects, and that is also very important. One of the tasks that I could say using 2D object detection is like, where is the free space? If you can find the free space, then the vehicle can move around freely, right? So that is where the free space detection is one of the tasks that can be done using the output of 2D semantic segmentation. The other task that can be done using the camera sensor is the traffic light detection. Again, it is one of the parts that you can do with the 2D object detection also. Like in this image, you can see different kinds of objects are detected, but apart from that, you can also detect the traffic light. But another part that can be done is that what kind of light it is, whether it is green light, yellow light, or red light, and based on that, decision will be taken whether to stop the vehicle, whether to run the vehicle, whether to slow down the vehicle. All the decision can be done using the traffic light detection. Then there is a part called as lane or flow detection. Actually, it detects the drivable area where the vehicle could be driven between these two lines. If you have two lines like this, then you need to know where the vehicle could move. Actually, to run this kind of algorithm, there is a famous algorithm called as vanishing point algorithm, where we try to find where the parallel lines should meet. But in general, the parallel lines don't meet, right? But when you are thinking about, let's say you are in a digit kind of scenario where you have the roads, and you can see that the roads will look like they are meeting at infinity, right? So that infinity point where the parallel lines meet is known as the vanishing point. Now if you are moving between two lanes and you try to keep that vanishing point actually on the middle of the image, then you will see that the vehicle would generally move on the middle of these two lanes, right? So for this, generally there are many algorithms nowadays which can work on deep learning to find out that vanishing point, and based on that we can actually move the vehicle. But in general, very simple mathematical algorithms like the Hopf transformation and everything can actually help you to find out the vanishing point. Okay. Another important task is the object tracking, because only object detection is not going to help. Like I told you, in case of perception, the whole point is like detection, localization, and trajectory. So trajectory can only be find out if you know the tracks of different vehicles. That means each of these vehicles that we have detected needs to be given one identification. Like for example, some person comes to my room, I would say that a person came. But if I know the name, then I would say that X person came. So that X is the identification that I give. So from there on, wherever he moves in this scenario, I would say that X is moving. So I can find out the trajectory of X. Similar to that, only finding so there would be multiples of cars. So just by saying that the car has this trajectory, it is very confusing. I can't know which car is moving. So each of these cars, let's say there are multiples of cars that you encounter in a scenario, each of these cars needs to be given an identification number. So that is where it is done by object tracking, using this research area called as object tracking. We generally use different kinds of filtering algorithms like this Kalman filtering, then different variations of Kalman filtering like this uncentered Kalman filter, then extended Kalman filter. All these algorithms are being used to actually track track different kinds of vehicles on the road. All right, so that is the area which is known as 2D object tracking. So using camera, we can do different kind of tasks that we already discussed, like 2D object detection, semantic segmentation, traffic light detection, lane following, 2D object tracking. Right, and you will see that basis of most of these algorithms is deep learning, because you can see object detection, semantic segmentation, and traffic light detection. Everything needs object detection, and for this object tracking, object detection output is the input. Okay, so for 2D object tracking, actually the input is the output of 2D object detection. So first thing first, we need to do the object detection. We need to detect different kinds of objects on the road, and their famous deep learning algorithms like this convolutional neural networks, as we already discussed, like this YOLO algorithm, RCNN based algorithm, this single shot detector algorithm, everything is being used. Now as I told you, like in case of camera sensor, the biggest problem is that we can't find out the depth. And when it comes to a autonomous vehicle scenario, or in general in any robotic scenario, we need to actually know the 3D information. Without 3D information, it is of no use, right? Because if we don't know where the vehicle is with respect to the autonomous vehicle in terms of distance, it is going to be very difficult. So that is where, to work on the drawback of the camera sensor, there is a famous sensor known as light detection and ranging, or the LiDAR sensor comes out. So how this LiDAR sensor works is that it sends out very short light pulses at different angles. So these light pulses are the laser sensors, right? So laser beam is being emitted at definite short intervals, and that laser beam actually rotates in the vertical plane from some, let's say, minus 15 degree to plus 15 degree. It will rotate in a vertical plane in a spiral way, and as it rotates, it will go, that laser beam will go, hit and come back, and wherever it hits on the in the environment, it will create a point over there. That is why the output of a LiDAR sensor is known as a point cloud. So you'll get lots of points. So you can see, if you compare with the camera sensor, which is a continuous sensor, for every pixel you will have some value in case of a camera sensor. But in case of LiDAR, you can have very sparse values, because it can only generate a point wherever it hits some object. Wherever it doesn't hit, it will just create a hollow part. Even it might happen that because of the short pulses, you will get many points as like blank points. So that is why it is a point cloud. It is not very dense. It is just a points all over the environment. Wherever it hits, it will create a point over there. But the biggest advantage being that it is in 3D. So that is the advantage. It can give you 3D information. The disadvantage is that it is a sparse data if you compare with the camera sensor. Also, it is very costly. Believe me, the lowest resolution, like we define the resolution of a camera in terms like width multiplied by height, we can define the laser sensor, LiDAR sensor resolution in terms of the how many rotations it makes in the vertical plane. If it makes less number of rotations, the resolution is less. Generally, the resolutions are defined by 16 scan line, 32 scan line, 64 scan line, 128 scan line. So, like we define that. And believe me, the lowest resolution sensor, which is like 16 scan line sensor, can cost you around 5 to 6 lakhs. I have one LiDAR sensor which I can show you. You see, if you are able to see it, that you can see. This is one of the LiDAR sensor from a company called as Oyster. So here it is a 32 scan line LiDAR, and it costed me around 8 lakhs. So that is how costly it is. And the data, so here you can see, this is the part where it collects the data in the 360 degree, and the LiDAR sensor moves in the vertical plane from some angle to some angle, sometimes minus 50 to 15 to plus 15, like that, right? So based on like how many rotations it makes, it will create these scan lines, and those scan lines will actually contain your point cloud data. So this is the output of a LiDAR sensor. Although the LiDAR sensor, I am able to show it in a 2D plane like on my screen. Generally, it is not like that. Generally, it gives you point clouds. So it is just a visual representation of the data that is coming out of it. So you can see the around the vehicle, there is no data, because as I told you, generally the LiDAR sensor is placed on the top. So top means the whatever in the near vicinity, it will not be able to collect. So that is why it can give you after some distance. So from there, there on, it wherever the scan line, you can see these are the scan lines, the concentric circles that you are getting. Wherever it hits, it will create a point. You can see there is some truck that looks like, or you can think there is a car. Okay, it looks like a car. So wherever it hits, it will go and come back. So whatever is there behind this, it will not be able to find out. So that is where you get all these points, and this environment is known as a point cloud environment. Okay, and these LiDAR sensors can give you data up to like 400 meters. Like this LiDAR sensor I have bought, it can give me up to 200 meters. If you go for higher resolution LiDAR, it can give you data up to 400 meters. Some researchers, like if you go to the Tesla autonomous vehicles, they are because of actually because of this LiDARs, the cost of the autonomous vehicles is going to be very high. So the Tesla is working on some technology by which they completely want to remove the part of LiDAR. They just want to do on the cameras. But the biggest problem with these cameras is that if we, let's say, if you use stereo camera, like some of you must have known, if you use two cameras by at some distance, we can actually find out the depth to some extent. You can approximate the depth using a concept called strangulation. But the problem with this kind of approaches, if you use multiple cameras and try to find out the depth information or the point cloud information or depth map of the whole 360 degree, we can actually do it up to like 10-20 meters, not more than that. But in case of an autonomous vehicle, we can at least need the data up to 30-40 meters in the surrounding of the vehicle. So that is where the problem is. But let's say in future some cameras come where we can get information most accurately up to 50 meters, where we can what do you say, merge two camera information like a stereo camera and get the depth information. Then definitely this lidar sensor can be replaced in future. But currently, apart from Tesla, most of the other companies are working on this lidar technology to actually find out the depth information. What we can do, we can actually do the 3D object detection, because we can get the 3D point cloud data. Now this 3D point cloud data, like in case of a camera, we generally pass the what do you say, intensity information. So that intensity information is going through different neural networks to give you the output, right? So in case of 3D object detection, whatever the XYZ values or the point cloud values, each point will be having its own X value, Y value, Z value. Even along with that, it will have some angle also. So all this information is being passed through the different neural networks like the convolutional networks to actually get the 3D object detection. So the difference between the 2D object detection and 3D object detection is that in case of 2D object detection, as I already explained, we can get what kind of object it is and what is its bounding box in the camera plane. But in case of 3D object detection, we get what kind of object it is, right? So that is always there, but we get a 3D bounding box. That means apart from your just length and height, sorry, width and height, you will have a width, height and length, and along with that you will have the centroid of the object. So you will have XYZ information along with that width and height and length information. Not only that, you will have an angle also, at what angle the object is with respect to the autonomous vehicle. So you see three information for the centroid, three information for width, height and length, and one information for the angle and what kind of object it is. So 3 plus 3 plus 1 plus 1. So you get essentially 8 information in case of an 3D object detection. So your the output in case of your deep learning will have 8 information coming. Of course, it is a classification as well as regression problem. So towards the end of your deep neural network, you will find two heads. One head to find out what kind of object it is, other head to actually find out the bounding box information. So it is the part which actually the output part which actually does the object detection, object type detection, that is the classification head, and the part where actually the regression part is done, that is where you will actually find out the different information like where the the centroid of the object along with that width, height and length, and at what angle it is with respect to the autonomous vehicle, right? So that is the 3D object detection in whole. But the problem with this kind of object detection models is requires heavy processing as compared to camera based object detection. Camera based object detection, as I told you, this YOLO object detection is very fast. It can give you real time information, right? But in case of lidar, it is very difficult to do, right? So we are coming up with algorithms which can actually work in real time. That is where the research lies in case of lidar. So this is the example or output of a 3D object detection. This is the vehicle that we are driving and we are getting the lidar data, and you can see all this is what is the 3D object detection. You get actually 3D bounding boxes in and around the vehicles, right? So this is from one of the research papers. Then there is radar sensor. So in the interest of time, I will be a little bit fast for this kind of sensor, because most specifically the most important sensors are this camera and lidar sensor. So most of the research you will see this object detection and everything that is generally done using this camera and lidar. Radar is very efficient with low cost and small footprint. If you compare with the camera lidar sensor, it is low cost, but again the resolution would be very less. Its sensitivity in dark and poor weather conditions also helps to cover the domains with when lidar and camera might fail. Okay, it works on the principle of electromagnetic waves. So if you compare with the lidar, its advantage is it operates in wet weather conditions, low cost and accurate velocity detection, which we are not able to do in case of lidar. But con is low resolution. So it has very low resolution. It can't give you the data like a lidar can. So you see, lidar has its own disadvantage, even radar has its own disadvantage. So we need to go to a technique where we can fuse both the lidar and radar data. So that is very important. Now then there are passive sensors like the GPS and IMU. I already explained GPS can help you to put the vehicle in a global position with respect to others in the environment. So it can give you a latitude and longitude information which can actually help you to do the global localization. It doesn't give you any active information, like it doesn't directly interact with the, when I say directly interact with, it doesn't collect any information from surrounding environment. Okay, it can just help you to get where it is with respect to others in the global frame of reference, right? So that is where you get the latitude and longitude information. Inertial measurement unit, like you can get the acceleration of the vehicle. Okay, when I say vehicle, means own vehicle, the vehicle that we are trying to make autonomous, we can get the acceleration of data of that. Even we can get the heading of that vehicle. If we do that, if we use this information like acceleration and the heading of our own vehicle, then if we know the 3D object detection and 3D object tracking of different vehicles on the road, we can actually come up with some mathematical algorithm which can actually help you to find out the acceleration and velocity of other objects in the on the road, right? So that is where the IMU information is very much important. If you know your IMU information, you can actually approximate the IMU information of other objects on the road. Even if you know the IMU information, you can know the, like for example, if you know the GPS location of our own vehicle, then you can actually, even if you don't know the GPS of others vehicles on the road, you can actually approximate their values by using the distance and all. There are different algorithms for that, right? So in that sense, the GPS and IMU also plays a very important role. Now coming to the part, I will be little bit fast, is we are nearing time. So the other part is the multi-sensor fusion, where we try to like combine data from different sensors. Like as I told you, some sensors have their own disadvantages and advantages. So each sensor works on the drawback of the others. So that is where the multi-sensor fusion is very important. And one of the what do you say, most researched area is the camera plus lidar fusion, because you can see camera is at a different place, lidar is at a different place, so they have their own transformations, right? So they have their own translation, scaling, and rotation, and even they can be at different angles. So the problem is like camera follows its own frame of reference. Even the camera, like in case of a data set that we are using, kitty data set, camera is like the x-axis towards the right and y is towards the down. In case of lidar, the x is towards the front, y is towards the left, z is towards the down. So they have their own frame of references, they have their own positions. So that is the biggest problem. Now the whole problem is how to bring all of the sensors to a common field of reference. So that is where we need to know the calibration information between these two sensors. That is a engineering problem, I can accept that, but even though it's an engineering problem, it's a very difficult one, because every time you place your sensors on the autonomous vehicle, the position changes to some extent, right? Even though you try to put it edge, accurate edge, you can still, you will have some what do you say, problems. So that's why you need to calibrate these two sensors. That is where the external calibration plays a very important role. And once you do the external calibration, then only you can transform the data from one plane to the other plane, or you can bring to actually a common coordinate system like the car coordinate system. So this is one of the images where you can see the camera and lidar data is properly aligned. That means we have done the fusion. If it is not fused together, you will see that the lidar data would be visible somewhere over here, like this. You are getting this kind of image in from the lidar, right? So that will be somewhere over at the top. Now to align them properly, we need to actually do the calibration, proper calibration. If we do that, then only we can fuse the data, and fused data can be actually passed to the different deep neural network algorithms to give you a better information. Okay, so that is where the fusion algorithms are very important. Actually 3D multi-object tracking, like we can extend the whatever we discussed in 2D object tracking to 3D multi-object tracking, that is generally done on the fusion data of camera and lidar. Different data sets in this area, if we see, generally we start with the data set called as kitty data set. That is one of the very famous data set that was proposed in the year of 2012 itself, but now they have proposed their own another data set like kitty 360. But apart from that, there are other data set like NuScenes, Waymo, Argoverse, Apolloscape, everything is there. But when it comes to Indian scenarios, there is a data set called as IDT, or Indian driving data set is there. Now coming to the challenges, there are like everything that I discussed, all these parts that for camera, lidar, and everything is a research area of its own, like 2D object detection and tracking, 3D object detection and tracking, lane following, lidar and image segmentation, traffic light detection, localization, even lidar and camera fusion, like how to pass the fusion data through different deep learning algorithms to come up with better accurate object detection. That is also one point is there. Even tracking can be done using the fusion data, right? So that is where there are many challenges in the domain of autonomous vehicle. And as I told you from my starting slides, that it is a area that is grooming, right? There are, so it is going to be realistic in few years, right? So that is where the research is its like initial stages. I would not say initial. We have reached to a certain stage. It started in the year of 2016 or 17, but still there is so much of research that lies, and more specifically, the research lies in how we can actually do all of this in Indian scenarios. That is the biggest problem, right? So that is where all of these challenges can be taken up. Those who want to work in this research area, right? So yeah, so this is one of the demos where you can see the 3D object detection, even 2D object detection, and we can do the tracking or localization. Okay, so I didn't have time, or else I would have shown the video. So all of these things we discussed in today's. So this is just a summary what we can do. Like using camera, we can do the object detection and 2D object tracking. We can do the traffic light detection using LiDAR. We can do the point cloud processing to do 3D object detection and tracking. Using radar, we can process the radar data to do radar object tracking. At the end, we can again fuse the data to get better accurate information. Right. So this is all we discussed in today's talk. Yeah. So this brings to the end of my talk. So if there are any participants, I would like to take few questions. Sir, am I audible?
Yes, sir. Yes, sir. Audible, sir.
Okay. So are there any participants? Because I am not able to see any participants.
Yes, sir. So now I request to the participants, if you have any doubt, then now sir is with us. So ask
Yes.
any doubt, or you can write on the chat box.
That is also fine.
Okay.
Actually, 1 hour talk is very less for this kind of topics, but still I tried to give you a superficial understanding of what is an autonomous vehicle and what are the tasks that we can do. And most of the tasks that I will discuss, right, can be done using the technology of deep learning, right? So that is how it is. So if there are any questions, you can write in the chat box also.
Yes, sir. Yes. So thanks, sir. I hope
Yeah.
there is no question, so we can end up the session. Thank you for coming and
Yeah.
accepting our invitation, sir. Thank you very
Yeah.
much.
Yeah. Thank you, sir, for inviting me for this talk. Thank you very much.
Thank you. Thank you very much.
Bye,
Okay.
sir.
Thank you.